Hi everyone, today we're going to learn about binary exponentiation. So for now, just ignore the title of this video and we'll jump into a problem. So the problem is pretty simple. It's given a and b, find a to the power b. This simple problem also has a very simple algorithm. The algorithm is just to multiply a by itself b number of times, right? That's basically the definition of a to the power b. The way to do that in code is pretty simple. You just have a variable prod which is initialized to 1, and then you loop b times, and inside the loop you just keep multiplying prod by a, right? So the first time the loop runs, you get prod is equal to a at the end of it. The second time the loop runs, you get prod is equal to a squared at the end of it, and so on, right? So if you loop b number of times, you get a prod is equal to a to the power b in the end. That's the pretty simple algorithm for this question. Uh, but since we're looping b number of times, the time complexity of this algorithm is big O of b, right? So can we do something better than this? So let's try to do that. Let's first try to see some kind of a recursive approach and see if that helps us. Okay. So the recursive approach we'll try now is based on this recurrence relation or this mathematical equation that a to the power b is equal to a times a to the power b minus 1, right? This uh, recurrence relation or this mathematical equation gives us inherently a recursive approach, right? In which a to the power b is, which was actually our problem, is now broken down into a sub problem, which is a to the power b minus 1, right? Along with this, we also know that a to the power 0 is equal to 1 for any a. So this can be our base case, right? Now, based on this, based on these facts, we can build basically our recursive function power of a comma b, which basically calculates a to the power b, right? And this recursive function, first we write our base cases. So if b is equal to 0, then we return 1. But if b isn't 0, then what we need to do is uh, we can directly say that answer is going to be equal to a into power of a comma b minus 1, right? This is exactly what the recurrence relation that's written in the first line of this slide uh, says. It's just written in code. So answer is equal to a times power of a comma b minus 1, right? And then we can just return this answer. So that's basically our recursive function. What's the time complexity of this? So the time complexity for this recursive function is going to be the number of times this recursive function is called into the uh, the time taken to execute each recursive call, right? So the number of times this recursive function is called is going to be b, right? Because we're basically making a recursive call in which b is reduced by 1 every time, and the base case is when b is equal to 0, right? So if the first call we make is power of a comma b, the next call we make is going to be power of a comma b minus 1, and the call after that we make is going to be power of a comma b minus 2, and so on till b becomes 0, right? So that's going to be a total of b recursive calls. Apart from that, in each uh, recursive call, the operations that are being done are just simple constant time operations, right? So the total time complexity of this is just going to be big O of b. We still end up getting the same time complexity that we had with our simple algorithm. So this doesn't help us much. But this idea of thinking recursively about the problem might help us come up with a better approach. So let's try to improve this approach that we just had by noticing that in case b is ever even, right, we can break it down like this. We can say a to the power b is equal to a to the power b by 2 squared. In this case, again, your problem is going to be the left hand side of this equation, which is a to the power b, and the sub problem is calculating a to the power b by 2, because if you calculate a to the power b by 2 as your sub problem, you can simply multiply it with itself to get the answer to your problem, right? Now, what happens if b is odd? If b is odd, we can simply use the same recursive relation that we were using in our previous approach, and that's it, right? So this recursive approach should be a little better, right? Because for even b's, we have a much smaller sub problem now, right? We've reduced the power that we need to calculate by half instead of reducing it by 1, right? But this is only for even b's, right? Not for odd b's. It might seem that that is a problem, but if you look at if you look at this formulation more closely, you'll observe that b minus 1 is actually going to be even, right? If b is odd, b minus 1 is going to be even. And since b minus 1 is even, in just the next sub problem, that is in calculating a to the power b minus 1, you can use the first recurrence relation, and again you'll get a sub problem which is half, right? So this approach seems to actually be better than our previous approach, in which we were reducing b by just 1 in our sub problem. Here we can kind of reduce b by half, right, in 2 steps, say. So let's try to write the function for this now. So the first thing, again, what we're going to do is have our base case, which is going to be the same as the previous base case. If b is 0, then you return 1, right? Otherwise, what we need to do is we need to check if b is odd or even. So for that, we say if b mod 2 is 0, which means if b is even, then we calculate the answer for our sub problem, right? So we can do that by saying sub 1 is equal to power of a comma b by 2, right? And the answer to our current problem will just be sub 1 into sub 1, right? Or sub 1 squared. And then we can return this answer, okay? But if b isn't even, that means if b is odd, then the answer can simply be a into power of a comma b minus 1, which is basically the previous approach that we had used. And then we can return answers, okay? So that's our whole recursive function for the solution to this problem. Now let's try to kind of calculate the time complexity of this and see if this approach is actually better than our previous approach. So the time complexity of power of a comma b is like we'll calculate this based on one simple observation that we've made before, that in at most 2 function calls you can reduce b into b by 2, right? The problem of calculating power of a comma b can be reduced to the problem of calculating power of a comma b by 2, or in other words, the floor of b by 2, in at most 2 function calls, right? And the logic for that is that if b is even, then we straight away know that the sub problem we have is power of a comma b by 2, right? But if b is odd, right, then we first then we first solve the sub problem of power of a comma b minus 1, right? That has one function call, but b minus 1 is going to be even, right? So in solving that sub problem of power of a comma b minus 1, we can we'll need to solve the subproblem of power of a comma b minus 1 upon 2, right? So in two function calls, at most, we can reduce the size of our problem by half, right? And this is the key idea behind calculating the time complexity of this function, right? So let's try to calculate how many uh, steps it'll take for b to become 1 if we keep dividing it by 2. Okay, so if you keep dividing it by 2, let's say you divide it by 2 n times, so you get b over 2 to the power n, and this should be equal to 1, right? This basically tells us that n is equal to log b base 2, right? If you solve this equation, what you'll get is n is equal to log b base 2. So this is the number of times that you need to divide b by 2 to make it equal to 1, right? But to divide b by 2 once, you make two function calls at most, right? So in the worst case, what you'll be doing is making 2 into n function calls, right? Additionally, since our base case isn't b being 1, but it's b being 0, we'll make a final function call in which we do power of a comma b minus 1, which is 1 minus 1, to make b equal to 0, right? So the total number of function calls that we make is 2 into n plus 1, right? Where n is log 2b. So this means that and since this is the number of function calls we make, in each function we basically have some constant time operations, right? So the total time complexity of the whole recursive function is going to be the number of function calls times the time for each function, right? Which is simply equal to the total number of function calls, right? So that's going to be big O of 2 into log b plus 1, right? And this is equal to the big O of log b. So the time complexity of this function that we've created now, this better recursive approach, is big O of log b. And that's much better than big O of b, right? It's much better than a linear time. So this recursive algorithm that we've developed that calculates a to the power b in log b time is what's known as binary exponentiation. Okay, that's where the title of this video comes from. So now that we've learned about this algorithm and we've written even pseudocode for it, let's go ahead and try to actually code it up in our editor.
Right. So we're going to solve the binary exponentiation problem by solving this Leetcode question, which basically asks us to do the same thing. So calculate x raised to the power n, right? The only small caveat here is that the algorithm that we discussed assumes that the exponent n in this case is going to be greater than or equal to 0, right? We've only described the algorithm which deals with positive exponents. But in this question, you can have values of n that can be negative 2, which is seen in this third example here, where n is equal to minus 2, right? But this isn't such a big problem because if we just look at the same example here, 2 to the power minus 2 is nothing but 1 over 2 to the power 2, right? So we can handle those negative exponents by uh, just doing 1 over 2 to the power absolute of that negative exponent, right? Sorry, not 2 to the power, x to the power, the absolute of that negative exponent. So that should be pretty simple. So let's start off by coding up the function that we actually described, right? The binary exponentiation function, which is power of a comma b, right? And like we said, our base case is if b is 0, then we should just return 1, right? If b isn't 0, then we need to make a check if b is odd or even, right? In the case that b is even, what we do is we solve the sub problem of power a comma b by 2, right? And then we multiply the answer of this sub problem with itself to get the answer of the original problem, right? So answer is equal to sub 1 times sub 1, right? And then we can just return this answer simply. If b is odd, on the other hand, we have the simple recursive relation that we've described twice now, which is just that the answer is going to be a times the power of a comma b minus 1, right? And then we can simply return answer. So that's our whole uh, binary exponentiation recursive function, the recursive helper function which we'll use. Uh, so now what we need to do is, like I said, n could be negative in this case. So if the exponent that we have is positive, all we need to do is simply return the power of x to the power n, right? But otherwise, if n is negative, what we need to do is return 1 over the power of x to the, 1 over the power of x to the absolute of n, right? For example, in example 3 shown here, we had x as 2 and n as minus 2. So what our code would do is it would calculate 1 upon power of x, which is 2, to the power absolute of minus 2, which is 2. So that's the same thing that they've calculated here in this example. So that's what we basically put into code. That's the entirety of this solution. So let's just try to run it. Yeah, and it accepts on these sample cases. So we'll try to submit it. Yeah, and it works pretty well. As you can see, it has beats 98.7% of the other solutions. One thing that I would like to point out here is, since n can be any, like the absolute value of n can be till 2 to the power 31, uh, we could not have used the simple algorithm which takes big O of n time, uh, or the basic recursive algorithm which also takes big O of n time to solve this problem, right? The constraints don't allow that, because uh, the solution would just time out. So it would take too much time to process. You can try that yourself by simply coding the simple algorithm which loops b times or n times to calculate the power, and you'll see that you get something like a time limit exceeded error. That is why we need a better approach, which is this approach, which runs in log n time. So that's all for this video. Hope everything was clear. If you have any doubts, please leave them in the comments, and thank you for watching.